Hi everyone, in this video we're going to be looking at the lecture guide for Module 4. So this covers section 1.4, the last section that's on our exam. And this section is actually a pretty short one, which is really nice. It has one major idea here that's broken up into 3 parts. And so in this video we're going to look at all 3 parts of this idea and go through an example for each one. And then in a new video we're going to go over the example at the end of this that kind of brings everything together. So, what are we looking at today? Well, we're trying to look at how we can affect the strength of evidence in our problems. So, we're going to look at, okay, what can I change about a problem in order to make the p-value bigger or smaller, or the z-score bigger or smaller? And so we're going to look at what things can change, what their effect is, and then talk a little bit about why that's happening. So, how strong is my evidence? So let's look at this first factor here, and I'll read it actually before we do that. So it says, understand that a statistic that is further in the tail of the distribution will provide stronger evidence in support of the alternative. So, further in the tail, let's highlight it, will give us stronger evidence. So remember, the tails here, when we're talking about our chance model or our null distribution, means just further outside, more extreme. So you've got the main part and then you've got the tails going out. So let's actually check this out. So the first factor when we're looking at this, again, is how far in the tail is your statistic. So let's go back to Buzz and Doris. Remember, for Buzz and Doris, we had our null hypothesis was pi equals 0.5, or Buzz is just guessing. He goes up to the 2 buttons, he just jams one, he doesn't know what he's doing, he just hits one randomly. Or we thought actually Buzz and Doris are communicating and they should do better than 50%. Pi is greater than 0.5. That's our alternative. Okay, so here's what we're going to do. We're going to create a chance model for this scenario. Remember, what did we need to create this? We go to the applet. All we need to do is tell the applet, here's my null. Buzz and Doris did 16 total trials. I have to tell them the sample size as well. And then I have to just hit 100, 1,000, whatever I want to do. I did 1,000 for this one. So I've got the same distribution here. All that I've changed between these 3 pictures is my statistic. So in this scenario 1 here, this first one, I'm pretending that Buzz and Doris got it right 14 out of 16 times. So look at, this is pretty far into the tail of the distribution. Here's one of the tails. So we're pretty far into the tail. Well, what if we considered if actually Buzz and Doris got 12 out of 16? That's still in the tail, but it's a little closer to the middle. So compare 12 and 14. Okay, but what if they only got 10 out of 16? Again, it's still in the tail kind of, but it's a lot closer to the middle. So we've got 3 different statistics. And I think a lot of you are looking at this and going, more extreme, less extreme, even less extreme. And just by that, you're knowing what's going to happen with the strength of evidence. But let's just do the p-value so we can see. So in the little boxes here, I have the statistics for each of these and their p-values, which I got from just the applet counting the dots. And what do we notice? The statistic that's the most extreme, the furthest in the tail, has the smallest p-value. So further in the tail, smaller p-value. Okay, I get a little bit closer in to the middle, my p-value jumps up a little bit. Okay, I get even closer to the middle, and look, my p-value jumps up even more. So, what does that tell us? Well, we got to remember what the p-value tells us. So a small p-value means strong evidence for the alternative. So the smaller the p-value, the stronger the evidence. So as my statistic starts to move outside, move into the tail, move further into the tail, my evidence is getting stronger, stronger, stronger. So as I walk this way, my evidence is getting stronger, stronger, stronger. So how do we kind of wrap that all up into one sentence? As our statistic moves further into the tail, so if my statistic starts moving further into the tail out here, we get stronger evidence to support the alternative. Further into the tail, stronger evidence to support the alternative. And that should make sense, right? If Buzz and Doris were able to get 14 out of 16, you should be more convinced that they're actually communicating than if in a separate scenario, a different reality, they had only gotten 12 out of 16. You might look at that and go, okay, yeah, I mean, that's they'd have to be really lucky to get that still, so okay, I'm convinced. Even more so than if they got 10 out of 16. Then you're kind of thinking, well, maybe they just got lucky on this one. So further in the tail, the more extreme, in terms of how we were talking about this previously, the more evidence. So that's way number one. Your statistic can just be further in the tail. That could give you more evidence for your alternative. So that's one thing that can happen. Okay, well, what's the second thing? So the second thing that we can consider is we're actually going to keep the statistic the same. Don't change your statistic. Now what we're going to do is consider one-sided versus two-sided tests. So one-sided test versus two-sided. So what is this? Well, this is all about what we do choosing our alternative hypotheses. So a one-sided test means that we picked the greater than or less than symbol for our alternative. We know for some reason which direction we want to go here. If it was Buzz and Doris, we picked greater than because we knew if they're communicating, they should do good, right? They should do better than 50% because they're trying to get the fish. But there are other scenarios where maybe we don't know if the alternative to the null should be that it's the pi or mu or whatever we're looking at should be bigger or smaller. We don't know. So I've got two scenarios here, and we're going to create the same chance model. We're going to use the same statistic, but we're going to see what our evidence looks like if we, in scenario 1, we're trying to find evidence of greater than, versus scenario 2, not equal to. So what are we looking at here? We're looking at Yummies again, the candy bar. Remember, there were 3 candy bars. Yummies is one of them. And we were trying to find evidence of whether or not Yummies was getting that equal share, 1/3 of all purchases. Or, in this scenario, we're trying to find evidence that they're actually better than 1/3, right? We're Yummies company, and we're trying to say ours is better, people like ours better. So we're trying to find evidence of that. Or, in this scenario, we're just trying to figure out if it's different than 1/3. We don't know if it should be better or worse. We're trying to find evidence of either of those two. That's going to be important. That's why I'm stressing that. We're trying to find evidence of 2 different scenarios. So, we create a null distribution for both examples. And what's going on here? They look the same. Well, remember, how do we get this null distribution, this chance model? We tell the computer, this is my null hypothesis. Look, it's the same for both. Then we tell the computer the sample size. It's the same thing for both. We're not changing anything about the sample or the statistic. So they have the same null distribution. Okay, so then what do we do? Well, what we have to do is we have to go find our statistic. I'm doing this just in the applet. Boom, boom. Look, it's found our statistic of 34%. So just remind yourself, Yummies had 34% of the candy bar sales. Okay? But here's the difference. When I draw this line at 34% here, and this is a little bit weird, there's some rounding errors because these numbers have so many decimal places in them. So don't worry about this. This is just bad rounding. 34 is right here. So it finds 34%, and then because we said greater than in the alternative, all I'm going to do is look at that point and write. I count up the dots there and write because it was greater than. That's one-sided. Two-sided, I'm interested in all of the samples, all the dots that were as extreme as my statistic, 34%, or more extreme. But what do I mean more extreme? I mean it could be more extreme bigger than, but I also, remember, go back here, I'm also interested in evidence that Yummies is doing worse than the competition. So when I'm trying to compute this p-value, I need to be thinking to myself, okay, extreme could include big numbers where Yummies is better, or small numbers, Yummies is worse. I want to take both of these extremes and count all of those as evidence. So that's going to be a little weird because it makes it sound like what I'm saying is we've got more evidence. But watch what's going to happen. We count up these dots. We count up these dots, right? We add them together, divide by 1,000. We get 3.6% of all the samples were as extreme or more extreme than our sample. So that's right here. But in this case, we only had 1.8% of all samples be that extreme or more extreme. And so what's happening here? Go back to the p-value. Smaller p-value, stronger evidence. So even though we had the same statistic, the same sample size, the same null hypothesis, the same chance model, because we went from one-sided to two-sided, we actually ended up with not as strong evidence in the two-sided case. So this is stronger evidence than this. So let's say it in all together. The two-sided test has a larger p-value. That's bad for us. This means it's weaker evidence. Bigger p-value, bad for us. Weaker evidence. So this is weird. This is the weirdest of all of the two. Or of the three, sorry. So this is the weirdest one. But what are we trying to say here? So I think one way to think about this in terms of not even just like a mathy way necessarily, but just thinking about what we're doing. So what are we trying to prove or show here? We're looking for evidence for the alternative, okay? So if your alternative is two-sided, right, two-sided alternative, then that same statistic that you have, that's your evidence, right? Your evidence is the statistic that you have. So that evidence you have, the statistic, it's almost like it's doing double duty. You're trying to show both the possibility of greater than and less than all together using this one piece of evidence, this one statistic. And so over here, the full weight of that statistic all goes in, the full weight of that evidence all goes into showing this one thing. But in the two-sided case, what you're doing is you're splitting up that evidence into two different things you're trying to prove, right? It's like you're splitting the strength up between these two options. And so altogether, because you're splitting that up, you're weakening the overall ability to show that this is true. Because you're trying to show two things could be true now, but you haven't increased your evidence. Your statistic is just as extreme as before, right? It's just as far from the middle. Everything we talked about there, the z-score is still the same number, right? So it's still just as extreme as it was before, but now you're trying to use it to show two different things, okay? Or find evidence of two different things. So you're increasing the amount of things, you're doubling the number of things that you're trying to find evidence for, so that evidence is not going to go quite as far as it would if you're only trying to show one thing. All right? So there you go. What do we have to remember? Two-sided test is less overall evidence, less strength than a one-sided test. Two-sided test, less strong than a one-sided test. All right, so factor number 3. Factor number 3 is one that we already actually talked about last week. I kind of tried to start to get you thinking about this a little, and that's the sample size. If we were to hold everything else constant, don't change your null, don't change your statistic value. So if we're talking about proportions, I mean the percent will stay the same. Don't switch from one-sided to two-sided. Just stick with one of them. If everything else is the same and you increase the sample size, that will provide you stronger evidence. So what's the scenario, just as our quick example? Daisy's trying out for the DNBA. The only thing between her and her basketball dream is to show the coaches that she can make greater than 50% of her shots. She can show that, not necessarily prove 100%, but give them evidence that she can do that, then she's on the team. So let's set up our hypotheses. The null is Daisy's a 50% shooter. Pi equals 0.5, she can hit 50%. If that's what we end up thinking at the end of this, she doesn't make the team. But if we have evidence for the alternative, she's greater than 50%, then she can make the team. So the first question I want you to think about here, just to kind of get you really started with this is, okay, let's say you're Daisy, and you know you're better than 50% with your shots. Like, you know it's true. What would be better for you, to take more or less shots in front of the coaches? What would you want to do? And I think it's pretty natural to say, well, I think I want to shoot more because I know I'm better, so let me just shoot more so I can show it more. I think that's something people would say, right? So to be more specific, if Daisy, the coaches gave Daisy the option, okay, well, this is your last chance, Daisy. Either you could take 25 shots or 50 shots right now. You get one of the two you got to pick now. Well, Daisy should pick 50 shots. So we'll explore why it would be better for her to take 50 shots. So let's look at two specific scenarios. Scenario 1, Daisy makes 16 out of 25 shots for a 64%, or for 64%. Daisy, in scenario 2, makes 32 out of 50 shots, but that's 64% again. So look, our statistic has not changed. So same statistic, both scenarios. What have we changed, though? We've changed the sample size, but it's the same statistic. So let's check this out. We're going to look at our two distributions, or two chance models here. Okay, they get the same middle because it's same null hypotheses. But remember what happened last week when we were doing this together. Because we increased the sample size, the distributions themselves have changed. This distribution for the 50 shots has gotten squished down a little bit, right? Its standard deviation has gotten smaller. It's more compact. Okay, so try to remember what we were talking about with that, but we can see it with the p-value. So because our null distribution here is more compact, that means the same statistic right here, the same 64%, boom, 64%, boom, 64%, the same statistic will seem more extreme in this case. So we talked about this last week. We saw that if you have a distribution, a chance model, that's a little more packed together, like this one is, then you're going to end up with the same statistic looking to you and actually being more extreme. What does it mean to be more extreme? It means you have a smaller p-value, and that's what happens. Look at this. My p-value is rounding 3%. Here, my p-value is 11%. So what happened? A smaller sample size with the same statistic. Now this works for proportions and means. I'm just using means here, but it doesn't matter. With a smaller sample size, the same proportion of shots made is weaker evidence. So how do we say that another way? Increasing the sample size will provide stronger evidence for the alternative. So what does that mean for us? The more people we can ask in a survey, the more shots Daisy can take, the better. And I think that we did a good job with this last week where, a lot of people were realizing, yeah, that makes sense, because when you do something more often, you have this ability to kind of counteract randomness a little bit. So there's still randomness in coin flips, things like that, right? But the more you do something, the more the overall statistic you're calculating will get closer and closer to the true actual parameter value. So if Daisy really knows I'm better than 50%, then it's good for her to take more shots, because even if she starts off bad, right? She first 5 shots, airball, airball, airball. That's not going to look good. But if she takes 50 overall and she's really better than 50%, then she can make up for that by shooting more. If she only takes 25, you have a little bit more chance of a bad run somewhere in your 25 meaning more. But if you go out all the way to 50, you'll kind of get that balancing effect where that randomness, those streaky, shots that you could take a couple in a row will kind of balance out. If you're not really very good, you would definitely want to take less shots, because that's your best chance to get really lucky and go on a run of your life and hit a couple in a row and get on the DWNBA team. So, boom, we've got it. Bigger sample size, stronger evidence. And I think that that's a natural thing, but I just wanted to be able to show you the pictures. And so here's a photograph of Daisy trying out. She can dunk. It's very impressive. Very nice. So in the next video, what we'll do is go through another big example together, just trying to show each of these things.